Hey folks, thought we'd take a look at another example of finding area in polar coordinates. This will be an example of a rose curve. So let's say you're asked to find the area of one petal of the curve produced by the polar equation r equals 4 sine 3 theta. Uh, Remember from class and what we've been stressing, the first thing you should do is fire up your calculator to make a graph. Remember, the first time you look at a graph of a polar equation, by default, I recommend making your theta min 0 and your theta max 2 pi. And here's what a graph looks like. This is from my TI-84 calculator. My x-axis goes from -6 to 6, and or -5 to 5. My y-axis goes from -5 to 5. So we're asked to find the area of any one of these three petals. I don't have a perfectly square viewing window, but all three are the same. They all three have the same area. Doesn't matter which one we find the area of, just find the area of one petal. So after we've done the graph, um, next thing we should do is let's find a theta range, like a theta min and a theta max, that would produce just one petal. Now notice that in the graph, each petal happens to hit or intersect the pole. So we can try to find a theta min and a theta max that will trace out one petal um, by by um, by letting r equal 0 in our polar equation. R equals 4 sine 3 theta. Remember, r is distance from the pole. So if you're at the pole, your distance from the pole, well, it better be 0. So if we take our polar equation and let r equal 0, this is just a straightforward trig equation to solve. 0 equals 4 sine 3 theta. Divide both sides by 4, and you have 0 equals sine 3 theta. Um, the angle argument here is 3 theta. Keep in mind, this is just saying the sine of what, and what is represented by 3 theta. The sine of what is equal to 0. Well, we know the sine of 0 is 0, the sine of pi is 0, the sine of 2 pi is 0, the sine of 3 pi is 0, etc. So that means that 3 theta can be replaced by any of these multiples of pi. And here's how I kind of look at it. On my first trip around the unit circle, I would get 0 and pi. The sine of 0 is 0, the sine of pi is 0. On my second trip around the unit circle, I would pick up 2 pi and 3 pi. And then on my third trip around the unit circle, I'd pick up 4 pi and 5 pi. And as a little trick, I need to make 3 trips around the unit circle because of the 3 that's right here. If this had been a 5 theta, I'd make a total of 5 trips around the unit circle. So how do I get the thetas? Well, to get theta, just divide everything here by 3, and we get theta is equal to 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, and 5 pi over 3. So those are the values of theta where the polar equation would intersect the pole. So what I always do, or I stress to do, is go ahead and use your calculator to redraw the polar equation using a theta. Here I'll use a theta min of 0 and a theta max of pi over 3. Those were two values that were in the list that we just came up with, solutions to the equation. And let's see if one petal is traced by making a theta min 0, theta max of pi over 3. So when I go into my calculator, I make theta min 0 and theta max pi over 3, and I redraw the polar equation, r equals 4 sine 3 theta. This is the graph that I get. Okay, now don't be misled in thinking, oh, it doesn't quite hit the pole here. You know, something's bad. It didn't produce the petal. No, that would be incorrect. This is a limitation of the graphing calculator. If I were to make a smaller theta step, I think I could get the graph to touch the pole. I'm not going to mess around with that. I'm not going to worry with that. I trust the trig. I trust my ability in solving that trig equation. So I do believe that a theta min of 0 to a theta max of pi over 3 does produce that petal that is living in quadrant 1. So that means all we have to do now is just compute the area. Uh, Remember, in the polar world, area is equal to 1/2 the integral from alpha to beta r squared d theta. So for this problem, it's 1/2 the integral from 0 to 3. That's what traced out that one petal. And then r was 4 sine 3 theta. So we have to take that r and square it. So if we go ahead and square what's inside here, we get a 16 sine squared 3 theta. If we rip the 16 out front, 1/2 times 16 gives us 8. Folks, as we saw a while ago, this is a trigonometric integral. It's a sine squared 3 theta. We have to remember the identity, the power reducing identity for sine squared x. Remember, sine squared x equals 1/2 times the quantity 1 minus cosine 2x. We're going to use that identity next. And when we do that, we have 8 times the integral 1/2 quantity 1 minus cosine 6 theta d theta. So using the power reducing identity on sine squared 3 theta gives us 1/2 quantity 1 minus cosine 6 theta d theta. Well, if I rip the 1/2 out front, it gives me this integral. And then if I go ahead and do a little bit of calculus, antiderivative of 1 is theta. Antiderivative of cosine 6 theta is 1/6 sine 6 theta. And now we just have to crank this through the fundamental theorem of calculus. So put the pi over 3 in, put the pi over 3 in, minus, then putting the 0 in gives us this mess. This last piece here, that will all become 0. The sine of 2 pi is 0, so it looks like we're just going to end up with the area being 4 pi over 3. So the area of one of those 3 petals is 4 pi over 3. What if we were asked to find the area that was enclosed by all 3 petals? Well, to get the area enclosed by all 3 petals, since we just determined the area enclosed by one petal was 4 pi over 3, to get the area enclosed by all 3, all you have to do is just multiply that result by 3. So the area of one petal, well, I multiply it by 3, that would give you the area of all that was enclosed by all 3 petals. Well, that's another example of finding area in polar coordinates. Hope that helps, and good luck with the homework. Thanks for watching.